Hey class, Mr. H here, going to try some 7.5 inverse trig functions. A good place to start on that is some algebra, just a little review of inverses, and then we'll link that to the trig functions. So what is the inverse of this function? F of x equals x cubed minus 1. Just a reminder from algebra, remember f of x is you can always think of as y as well. You'll see them both, right? They're just kind of two different notations. So think of them as the same thing. So we have x inputs and then f of x or y output. We can just fill out a table, right, to get this started. So if you plug in -2, we get -2 cubed, -8, -1, -9. Okay, so I'll do this kind of quickly, not waste your time too much here. You can verify my work, but those are the values you would get for your outputs if you were to plug in those x values. Okay, what does the inverse mean? Really, all inverse is you switch the x's and the y's, or you switch the inputs and the outputs. So outputs become inputs, inputs become outputs. So if I'm going to create a table of inputs and outputs, I'm just going to, my inputs are now those values, and the outputs are the inputs from the other table. Okay, and then I've created a table for my inverse. And then now notice the new notation, and it's also still y, but it's more descriptive here. F inverse is f to the power of -1. All right, that means inverse. Does not mean 1 over, like they're reciprocal, like it just means inverse, right? So that symbol to the power of -1 is the symbol for inverse. You could also come up with an equation for the inverse. I don't know if you remember doing that from algebra, but technically speaking, what you do is you start with the function, and then you put y in there instead of f of x. It's just easier to work this out that way. And the technique is you swap the x and the y. So the x goes where the y is, and the y goes where the x is, right? And then that's your inverse equation. And then it's best if you have it solved for y. So then you would now just algebraically solve this for y. So you would add 1 to both sides, which you would end up with this, right? And then to get y by itself, you would cube root both sides, right? So cube root of x plus 1 would equal y. And there would be your function. And then typically what you do is replace now y with the new notation. F inverse of x is the cube root of x plus 1. Okay, and you could verify then if you plugged in these values into that x, right, those would be your outputs, right? Okay, so there's your little history lesson on inverses, or review on inverses. You could also graph them. The property is that, here, right here, notice that if BA is on one of them, then AB is on the other, right? So it tends to, what happens in the graph is you have a reflection about that y equals x line. So you can see it over here. There's the function and its inverse graphed, and there's a mirror right along that y equals x line. It's a mirror reflection, okay? Now let's get to some trig. So what about the inverse of f of x equals sine x? We can just go about it the same way. We could get some outputs going. So if we plug in -pi/2, think on these, I always think unit circle. I'm visualizing it, right? That bottom of the unit circle, -pi/2, same place as 3pi/2, right? That's where the y value is -1, right? At -pi/4, fourth quadrant, you'd see a -√2/2. At 0, the y value is 0. Pi/4 is +√2/2, and +pi/2 is 1. Okay, so there's a quick mental plugging in the points. So of course, if we're now, look what happens if we get the inverse, we just swap the columns, right? So now your inputs are those points on the unit circle, and the outputs are angles. Okay, and I'm doing this in radians. You could do it in degrees as well. That's okay, but typically you'll see it done with radians, real numbers. Okay. So the idea then is when you're dealing with inverse trig functions, your inputs and outputs are reversed, right? Inputs are ratios of sides or points on the unit circle, and the outputs are angle measures. It's reversed from when we did the regular sign. Okay, we could also get the equation similar to how we did it with the algebra function. We would start with y equals sine x, and then the technique is you switch the x and the y. So the x goes there and the y goes there. And there's your inverse function. Now, typically what you try to do is then solve this for y. But this one, I don't know how to do that. I mean, algebraically, you can't. Y is kind of stuck in there inside that sine function. So what is y? I guess I could say it in words. Y is the angle whose sine is equal to x. Right? I mean, that's really what you're going to be using right there. Y is the angle whose sine is x. And the notation that's been invented for that is this: y equals sine inverse x. Okay, so there is your what you're going to see. Another notation is this: arc sine means the same thing. All right, so you'll see either of those. Both of those mean this. Right, so when you see sine inverse x, that's equal to the angle whose sine is x. We'll practice with that with some problems here on the next page, or at some point. Okay. Now you could also get the graph of the sine inverse. We won't focus on that too much, but some things to note about this. It's sort of the reflection along the y equals x line of the regular sine graph, but it's restricted. So the range only goes from negative pi over 2 to pi over 2. The reason for that is, if not, it would not be a function. Right? If this thing just kept on going, you'd go back that way, and then it wouldn't pass that vertical line test from algebra. So we don't do that, and we restrict it. Okay, so in the box, put it in a box is probably important. It's basically what I said above, but now with that detail. To find the exact value of sine inverse x, find the angle between, so in that range, between negative pi over 2 and pi over 2, or if you're in degrees, negative 90 and 90, whose sine is x. Okay, before we get to the examples, we could do cosine inverse very much the same way. It just has a little bit of a different range, but the wording is the same, just your answer is going to be between 0 and pi, or 0 and 180. Okay, and then there's the tangent inverse graph, and then that range is the same as the sine, except it's parentheses, notice, so you don't include the endpoints. Right? So it's between negative pi over 2 and pi over 2, but your answer will never be one of those. It's strictly between. Okay, to summarize that and also include some of the other trig functions, this would be helpful. Okay, so when I look at this graph, this chart, the domain is values are your inputs, right? What are you allowed to put in? Okay, and then the range, these are what your answers should be. Your answers should end up in that interval. Okay, and then to help, because you'll probably be using the unit circle to answer these, where should you look on the unit circle depending on the trig function? Okay, that has to do with the interval, but that interval is defined by those quadrants on the unit circle. Whew. Okay, how about we try some examples? Maybe fast forward to this point. Okay, I think it's helpful to use the unit circle on these examples. So I put the unit circle there. You have those in previous notes, but we'll refer to it a lot. So it's here as well. Okay, use the unit circle to find the exact value. So let's try number 1, sine inverse 1. Okay, so remember what that means. You're trying to figure out the angle whose sine is 1. Remember, the sine is the y coordinate on the unit circle. So you're just looking for a place where the y coordinate is 1. There it is, right there. So the answer, oops, I dropped my pen. The answer is the angle. Okay. If it doesn't specify, you can give it in radians or degrees. Look for in your homework, it'll specify which one it wants. Typically, if it doesn't say, just give the radians. So on all these, I'll give radian measures since I didn't say what to do, but this would equal pi over 2, final answer. So there's really not a lot of work to do on these, which is awesome, but you do have to use that unit circle and figure it out. Okay, how about arc sine, which is just sine inverse of 1/2. So I'm looking for a place where the y coordinate is 1/2. Oops, there's one. Okay, notice also 1/2 is over here. So it's actually 2 places on the unit circle. But remember, for the restriction for sine has to be between those angles, which means quadrants 1 and 4 only. So never go to quadrants 2 or 3 for sine. So you don't use that one, right? Only this one over here. Okay, so my answer is that angle, pi over 6. That's it. Okay. 5 pi over 6 is tempting, but it's wrong. How about sine inverse of negative root 2 over 2? All right, where is negative root 2 over 2? Remember, you're restricted to quadrants 1 and 4 for sine. So I got to go down to quadrant 4 because it's negative, and the y coordinate, negative root 2 over 2 is right there. So there's my answer, kind of. But here again, I have to be careful. 7 pi over 4 is wrong because, go back to my range, this. It has to be between negative pi over 2 and pi over 2. 7 pi over 4 is not in that. It's outside of that range. That means instead of giving 7 pi over 4, you have to give the negative version of that angle, or specifically, if I draw it out, oh, that was not very straight. That angle going in that direction, the negative angle, where that's equal to negative pi over 4, right? That's the coterminal angle to 7 pi over 4. It's negative pi over 4, right? I guess you could calculate that. I mean, if you're like, where is negative pi over 4 coming from? Oops, it's 7 pi over 4 minus 2 pi, right? Okay. Or think of it in degrees, might be a little easier with mental math, right? That's 315. So if you go that way, it's negative 45, which is negative pi over 4. Okay, so there's my final answer. All right. So, typically you can use the unit circle. The pitfalls are using a wrong quadrant or a wrong angle that's, not within the range. So use the closest way to get to that angle as opposed to the long way. And then you're going to be fine. How about some cosines? So cosine negative 1, cosine inverse 1. We got to look now for cosine. Those are x coordinates on the unit circle. So is there any x coordinates that are equal to 1? There's only one of them. This got all messy. Let's get rid of that. Start over. Right there, right? So that angle is 0. So my answer is 0 for that one. Okay. How about cosine inverse root 2 over 2? There it is. X coordinate root 2 over 2, answer pi over 4, or 45 degrees if they wanted degrees. And then negative root 3 over 2. Okay, so for cosine, remember its restriction is 0 to pi, or quadrants 1 and 2, right? So it's a little different for cosine, right? If we're looking at negative values, we're going to go to quadrant 2 and look for a negative root 3 over 2 on the x coordinate. There it is, okay? So in other words, I mean, there's another one over here, but you don't want to go there, right? That's outside of the range, right? So there's your pitfall. Don't go to quadrant 3. In general, you never use quadrant 3 for any of these, right? So quadrant 2 for cosine is where you got to go. And my answer is right there, 5 pi over 6. Okay. And that's a value between 0 and pi, so you're good. So we're going 5 pi over 6 for that one. Okay. How about tangent? Okay, so tangent, well, let's see, let's restart. Tangent, remember, let's just get some room here. Tangent is y over x, right? So you're trying to find a place on the unit circle where the ratio of y divided by x is 0, right? Which means then that the y would have to be 0, right? Because if the x is 0, you get undefined. So I'm looking for a place where the y is 0 and then x is whatever. Right? So is there any coordinate where the y is equal to 0? There it is, right? And so then there's tangent 0. And that's 0, there's your answer. Tangent 0 is 0. Lots of zeros. Circle it, looks like a 0 too. Okay, how about tangent inverse -1? All right. Any place where you're going to get tangent -1? Well, if tangent is 1, that means y and x would have to be the same, right? Because it's y divided by x. You need those to be equal to get a ratio of 1, but it's -1, right? So I'm going to look here for that. That's where the x and the y are the same, but one of them's positive and one of them is negative. And that's in quadrant 4. Let's see, can I use quadrant 4 for tangent? Yes. Tangent is the same as sine. So you're always going to be in quadrants 1 and 4. Okay. So there it is. It's again, one of those you have to be careful of, though. You don't want to give the answer of 7 pi over 4. You have to give the negative angle that's coterminal to that, which we found earlier is negative pi over 4. So the answer for this one is negative pi over 4. Okay, how about tangent inverse of √3/3? Tangent inverse of √3/3. It's positive, so that means in quadrant 1. And I need a ratio where I get √3/3. A good thing to know is √3/3 is the same as 1/√3, the unrationalized version, right? So those think of as interchangeable. Sometimes it's easier to use this one, like in this case, because if, again, y divided by x, we need that ratio to be 1/√3. So if I think about where that would be, it would be the y value with a 1 and the x value with a √3, right? Y value 1, x value √3. Remember, when you do the ratio, those denominators of 2 would cancel anyway. So there's where I am, right? So there's my tangent, and that angle would be pi over 6. Okay. Okay, so we're halfway done with those. I'm going to take a breather, stop there, and then we'll come back and do some other trig functions and see if that's any more complicated, but it's pretty much more of the same. All right, but continue on the next video. All right, hope you enjoyed it. Talk to you later.